So now we're going to learn about calorimetry, okay? And what exactly is calorimetry? So calorimetry is an experimental technique that we use to determine the enthalpy changes of certain reactions or certain processes, okay? Or how much energy they release or how much energy they take in, okay? So it is a method to determine energy changes for different processes or different reactions. So we're first going to see how we can determine the enthalpy change of combustion, okay? The enthalpy change of combustion using calorimetry. Okay? The enthalpy change of combustion has the following symbol, right? You have delta H for enthalpy change and then the subscript C for combustion. Okay, so this is the symbol for the enthalpy change of combustion. And this is defined as the enthalpy change, okay, the enthalpy change or energy change, the enthalpy change or energy change when 1 mole of a substance, okay, 1 mole of a substance is completely combusted, okay, is completely combusted right, in excess oxygen, in excess oxygen. Right? You can also say it is the energy released when 1 mole of a substance is completely combusted in excess oxygen, because it's always going to be exothermic. Okay, enthalpy changes of combustion are always exothermic. Right? So, for example, if we talk about the enthalpy change of combustion of different fuels, right? We can use calorimetry, for example, to determine how much energy is released when a certain amount of let's say octane is combusted, or a certain amount of methane is combusted. Right? Octane is used in cars as fuel. Methane is used in gas stoves as fuel. Right? So this calorimetry can give us information about how much energy is released. Okay, when these fuels are combusted, for example. Okay. There are other types of reactions that we can use calorimetry for, but we'll first be looking at combustion. Okay. So let's say I have this basic experimental setup. Here I have a fuel. Okay, this fuel is in a burner. Okay, with a wick, sort of like a candle, right? It's soaked in the fuel, right? And what I'm doing here is that I'm igniting that fuel, right? So combustion is taking place. Combustion is taking place, and that combustion is releasing energy, right? And here I have a calorimeter, which is my instrument, right? Normally in a lab, you'll be using a styrofoam cup or some sort of container, some sort of basic container in which you have water. Okay, and what I'm doing is I am combusting this fuel. This fuel is releasing energy, right? And most of that energy is being absorbed by the water, right? And I can monitor the temperature of the water, right? I know the initial temperature, right? And I can combust this fuel for a certain period of time, right? Let's say 10 minutes, for example, and then I can stop the reaction and I can figure out the final temperature. So I know the initial temperature, I know the final temperature, right? I can also determine how much fuel was combusted, right? By taking the initial mass of the burner and the final mass. So the measurements I can make here, okay? The measurements I can make here are the following, right? I can take the initial mass of fuel plus burner, right? I can take the final mass of fuel plus the burner, right? Burner is just the container in which we have the fuel, right? Obviously the mass of this mass will decrease, right? Because fuel is being combusted, it's reacting, right? So the difference will tell us how much fuel was consumed, right? I can also take the initial temperature of the water, right? And I also know the final temperature of the water. Right? In this case, the temperature of the water will increase because combustion is releasing energy, right, to the surroundings. So this water is sort of part of the surroundings, right? So this is releasing heat, releasing energy in the form of heat, and then the water itself is taking in heat from the fuel, right? So the water is the surroundings, right? Heat is lost from the from the system, that's your combustion reaction, to the surroundings, that is your water, right? So there's a transfer of heat from the fuel to the water. And another reading that we would take over here is the volume of water. Okay. Now the volume of water, okay, the volume of water in centimeter cube, okay, the volume of water in centimeter cube is equal to the mass in grams, okay, because water has a density of 1 gram per centimeter cube. So if you had, for example, 200 centimeter cube of water, that's the same as saying you have 200 grams of water. Okay, 1 centimeter cube has a mass of 1 gram, right? That's the density of water, 1 gram per centimeter cube. So these are the measurements that we would take. Okay, these are the measurements that we would take. Now the question is, if we look at the increase in temperature, right? If we look at the increase in temperature or the change in temperature, what does that depend on? So the increase in temperature, let's say that we have a given amount of fuel. Okay, so let's say we fix our amount of fuel. So let's say I'm using n moles of fuel here. Okay, whatever that is. Let's say I have a fixed amount of fuel, right? What does the increase in temperature depend on, or the change in temperature? Can I say that the change in temperature is directly proportional to the heat released, right? The greater the amount of heat released, the greater the rise in temperature, right? So it is directly proportional to the heat energy released, right? Q over here refers to the heat gained by the surroundings, right? Again, if you remember, Q is a reference to the heat energy gained by the surroundings, okay? We also know that the mass of water would have an effect on the rise in temperature, right? If we use double the mass of water, for example, the rise in temperature will be half as much. The greater the volume of water, the greater the mass of water, the lower the rise in temperature. So we can say that the rise in temperature is inversely proportional to the mass of water. And then we say that it's also inversely proportional to the specific heat capacity. The specific heat capacity, okay, the specific heat capacity, it has the symbol C, okay, lowercase c, refers to yes, the amount of energy needed to increase the temperature of 1 gram of a substance okay, by 1 degree Celsius or by 1 Kelvin. So the higher the heat capacity, the higher the specific heat capacity, the greater the amount of energy needed. Okay, so insulators have high specific heat capacities. Conductors have lower specific heat capacities. Lesser energy is needed to raise their temperature. So for example, a metal would have a lower specific heat capacity than water. Okay, and the specific heat capacity for water, is 4.18. Okay, 4.18 joules per gram per Kelvin. Okay, so 4.18 joules of energy are needed to raise the temperature of 1 gram of water by 1 Kelvin or 1 degree Celsius. So we can say that the rise in temperature is inversely proportional to the specific heat capacity. Right? Higher the heat capacity, the more energy that would be needed. So higher heat capacity would mean lower rise in temperature for a given amount of heat. So if you rearrange this expression, you get Q is equal to mc delta T. So in this expression here, okay, m is the mass of water in grams. Okay, it's the mass of water in grams. Okay, C is the specific heat capacity of water, 4.18 joules per gram per Kelvin. All right, and the change in temperature, okay, can be in Kelvin or degrees Celsius. Okay, it doesn't matter. So for example, let's say that my temperature changed from 20 degrees Celsius to, let's say, 80 degrees Celsius. Okay, the change in temperature would be 60 degrees Celsius. Okay, now the temperature in Kelvin, okay, the temperature in Kelvin is the temperature in degrees Celsius plus 273. Okay, temperature in Kelvin is equal to the temperature in degrees Celsius plus 273. Okay, so if the temperature in Celsius is changing from 20 degrees Celsius to 80 degrees Celsius, that's the same as saying the temperature in Kelvin is changing from 293 Kelvin to 373 53 Kelvin. But the change in temperature is still 60. Okay, so if you're using an expression in which we're using T, okay, just the temperature itself, then the units matter, whether it's degrees Celsius or Kelvin. But when we're talking about change in temperature or delta T, the units don't matter between Celsius and Kelvin. Okay, for Celsius and Kelvin, the change in temperature would be the same. All right, because it's a linear scale, right? There's just a plus 273 between the two. Okay, so the difference in temperature will remain the same. Okay, you can use Celsius or Kelvin to calculate changes in temperature, which is why the specific heat capacity of water can also be written as 4.18 joules per gram per degree Celsius. Okay, because again, the change in temperature doesn't matter, but okay, so you can say that, but we use Kelvin because that's the standard SI unit for temperature. Okay, so specific heat capacity is the amount of energy needed to increase the temperature of 1 gram of a substance by 1 Kelvin or by 1 degree Celsius. You're going to see data given to you in degrees Celsius or in Kelvin. Okay. So now let's do a question which we're going to calculate the enthalpy change of combustion of ethanol. Okay. The question says use the following experimental data to determine the enthalpy change when 1 mole of ethanol is burnt, okay, or completely combusted. So again, when we say the enthalpy change when 1 mole of ethanol is burnt, okay, that's the enthalpy change when 1 mole of a substance is completely combusted. Okay, that is called the enthalpy change of combustion. Okay, so here we have to calculate the enthalpy change of combustion of ethanol. So the first thing you do here is you would calculate the heat energy released into the water. Okay, you would calculate the heat energy released into the water. Okay, this is the basic experimental setup for what we're doing, right? We're combusting a fuel, right? Energy is being released, and the temperature of the water is rising. Okay, and we can calculate the amount of heat energy. We can calculate the amount of heat energy transferred to the water. Okay, we know that Q is equal to mc delta T. Okay, here Q will be in joules. All right, that's the heat energy. The mass of water that we're using is 150 grams. Okay, the specific heat capacity is 4.18, and the change in temperature is 45.7 minus 19.5, which is 26.2. So this comes out to 16427.4. Okay, so 16,427.4 joules of energy. Okay. Now we want to find the enthalpy change of combustion of ethanol. Okay, that is the enthalpy change when 1 mole of ethanol is completely combusted. Okay, now over here we know how much ethanol was combusted, right? You know how much ethanol was combusted, right? We know that the mass of fuel that was combusted in this case was the initial mass minus the final mass of the burner, right? That would be 121.67 minus 120.62, which is 1.05 grams. And again, we want to find the enthalpy change for 1 mole of ethanol being combusted, so we're going to convert this to moles, right? The mass is 1.05 grams, the mass of fuel, so we can say that the number of moles of fuel is equal to the mass over the molar mass, right? The mass of ethanol is 1.05 grams and the molar mass is 46. Okay, C2860, right? So the molar mass is 46 grams per mole. So then what is the number of moles of fuel that are being combusted in this experiment? So this comes out to 0.02283 moles of fuel. Okay, so this is the number of moles of ethanol that are being combusted. Okay, this is the number of moles of ethanol that are being combusted. Now the enthalpy change of combustion, okay, is the enthalpy change when 1 mole of ethanol is combusted, right? So over here we can say that 0.02283 moles being combusted, right, releases how much energy? 16,427.4. Okay, or in kilojoules that would be 16.427 kilojoules, right? So that is the amount of energy that we are releasing. That's the amount of energy that the system is releasing. So if Q is positive, then delta H would be negative. Okay, again, the system is releasing heat, the surroundings are gaining heat. So if Q is positive, delta H is negative. So we can say that 0.02283 moles of fuel being combusted releases negative 16.427 kilojoules of energy. Okay, again I've converted this to kilojoules by just dividing this by 1000. That's 16.427, and if Q is positive, surroundings are gaining heat, that means this is negative. Okay, the system releases this much heat. So then what is the heat that would be released if 1 mole of fuel was combusted, right? That is your enthalpy change of combustion. So here if you cross multiply, okay, you're going to get the enthalpy change of combustion. You're going to get the enthalpy change of combustion of ethanol as negative 720 kilojoules per mole, okay, to 3 significant figures. So that is the answer. Okay, that is the enthalpy change of combustion of ethanol. So to calculate the enthalpy change of combustion, okay, you can also just use the following expression. Okay, we can say that the enthalpy change of combustion is equal to minus Q. Okay, the enthalpy change of combustion is equal to minus mc delta T over 1000 N. Okay, again Q is equal to mc delta T, right? Q is equal to mc delta T, that is the heat gained by the surroundings. So that means that the heat released, or the enthalpy change for the system, will be negative if Q is positive. So that's minus mc delta T in joules, right? Then we divide by 1000, we convert the joules to kilojoules, and then we divide by the number of moles of fuel to get the enthalpy change per mole of fuel combusted. Okay, so in this case we were dividing negative mc delta T over 1000, that was minus 16.427, divided by the number of moles of fuel to get the enthalpy change of combustion. Okay, so this is minus Q over 1000 N. If over here obviously delta H is in kilojoules per mole. Okay, delta H is in kilojoules per mole, and Q over here is in joules. Okay, Q is in joules. N is the number of moles of fuel. Okay? Number of moles of fuel. Alternatively, what I prefer to do is I just prefer to convert the value of Q from joules to kilojoules first, and then I can just say that the enthalpy change of combustion is equal to minus Q over N. Okay, here we're taking Q in kilojoules, right? Here we're taking Q in kilojoules, and N is again the number of moles of fuel, right? So Q is taken in kilojoules, N is the number of moles of fuel, right? And delta H combustion is the enthalpy change of combustion in kilojoules per mole. Now let's look at the next question. Okay, the next question says a burner containing hexanol, that's C6H13OH, had a mass of 325.68 grams. It was lit and placed under a copper calorimeter containing 250 centimeter cube of water. The temperature of the water rose from 19.2 degrees Celsius to 31.6 degrees Celsius. Afterwards, the burner's mass was 324.37 grams. Calculate the heat evolved and then the enthalpy change of combustion for hexanol. So over here, right, we're first going to calculate the heat evolved. Okay, the heat evolved can be calculated using the expression Q is equal to mc delta T, right? The heat evolved Q will be calculated in joules. Okay, now M again is the mass of water. Okay, because it's water that we're heating, we have 250 centimeter cube of water, which is 250 grams. Okay, the volume in centimeter cube is the mass in grams for water. Okay, so we have 250 grams of water. Okay, the specific heat capacity is 4.18 joules per gram per Kelvin, and the change in temperature is 12.4 degrees Celsius, okay, which is just 12.4 Kelvin for delta T. So then Q is equal to 12,958 joules. Okay, so that is the heat evolved, okay, in joules. Now we need to find the enthalpy change of combustion for hexanol. Okay, and we're going to do that in kilojoules per mole. Okay, so we're first just going to convert Q. We know that Q is equal to 12.958 kilojoules, right? And we can say that the enthalpy change of combustion is simply minus Q over N, okay? And minus Q over N, where N is the number of moles of fuel, okay? N is the number of moles of fuel, right? So we can calculate the number of moles of fuel. We know the mass of fuel, right? The mass of fuel is 1.31 grams, right? So let's do that, right? We know the mass of fuel is the initial mass, which was initial minus final, right? Initial mass minus the final mass. The initial mass is 325.68. The final mass is 324.37. So that means 1.31 grams of fuel were combusted, which means that the number of moles of fuel is equal to the mass divided by the molar mass. So that is 1.31 divided by 102. Okay, that's the molar mass for hexanol, right? You have C6H14O. That's the molecular formula, right? 72 plus 14, 86 plus 16 is 102. So then we can say that we had 0.01284 moles of fuel that were combusted, right? So then per mole, right, that's the enthalpy change of combustion. It's the enthalpy change when one mole of a substance is completely combusted. We can say that per mole, right, we add minus 12.958. That's Q in kilojoules divided by the number of moles of fuel, which is 0.01284, and this is equal to, this comes out to negative 1010 kilojoules per mole, okay, to three significant figures. Minus 1010 kilojoules per mole, right, three significant figures. So that's our answer. All right, so this experimentally determined value is inaccurate, right? This experimentally determined value is inaccurate, and the reason why is because, okay, so we can say that the experimental, okay, the experimental value that we calculate, okay, calculated is inaccurate, all right, is inaccurate, and you're going to find that it's actually less exothermic, than the actual enthalpy change of combustion, okay. And the reason why is because, again, if you look at the experiment, we're assuming when we calculate Q, right, we're assuming that the amount of heat taken in by the water is equal to the amount of heat lost or amount of heat released by the combustion of fuel. But in actual fact, the amount of heat released is much greater. The actual amount of heat that the combustion of fuel releases is much greater than what we calculate experimentally. So you know, if the fuel is releasing a certain amount of energy, some of that energy is being absorbed by the water, whereas the rest of that energy is being released to the surroundings, right? So the calculated amount of heat energy is lesser than the actual amount of heat energy that was released, which means that Q should be more positive than what we calculated, right? Which means that the delta H will be more exothermic than what we calculated. So we can say that the biggest reason for this inaccuracy, the biggest reason is heat loss to the surroundings, okay? Heat loss to the surroundings. That's the major reason why the readings are inaccurate, okay? There are other reasons as well. Another reason that we have is we can have incomplete combustion of fuel, okay? Incomplete combustion releases lesser energy than complete combustion. All right, so we're assuming that we have complete combustion of fuel in our calculations. If we had incomplete combustion, lesser energy would have been, if we had incomplete combustion, lesser energy would have been released, right? We're assuming that we had complete combustion, right? But we may have had incomplete combustion, right? Another thing that can affect the accuracy of this experiment is impurities in the fuel, right? We're assuming that the fuel is 100% pure, right? So we're assuming that, for example, in the case of ethanol, we're assuming we have pure ethanol. Okay, there are no impurities present in fuel. If there were impurities, then obviously the enthalpy of combustion that you're calculating is not for pure ethanol. So these two factors, the fact that we have heat loss to the surroundings or that we may have incomplete combustion, make it less exothermic than the actual enthalpy change of combustion. Whereas the fact that there are impurities in fuel do affect the accuracy of the experiment, okay, or the calculated value compared to the actual value. There are improvements, of course, that we can make to improve the accuracy of this experiment, right? We can insulate the container, we can use a lid, okay, through which we can put the thermometer and so on, right? Those things will prevent or minimize heat loss to the surroundings, okay, which is the major factor when it comes to an inaccurate reading. Okay, so if you're asked to just list one reason, it'll always be heat loss to the surroundings, okay, for combustion experiments.